Hey everyone, it's time for physics. Today we start on Unit 10, Light. Well, the first question that we have to ask is, what is light? Let's do a simple experiment to see if we can figure out what it is. So what I'm going to do is I'm going to have a light source here, and I'm going to set it behind two barriers. These two barriers, I'm going to leave a little gap, a little opening to let that light go through. And we're going to see what happens on the other side in this area over here after we do that. So here I'm going to put my light down. Here are my two barriers. I'm going to set them down and we're going to see what comes out of the other side. There we go. As you can see, the light is not limited to just staying in this lane right here where the gap is. Instead, the light is allowed to bend all the way around the corners. Okay? So if we were to draw that on our diagram, it might look something like this. The light comes in, and then as it goes around the corner, it's able to bend out, and we get something that looks like that. Can you compare this to any other experience that you've had before? So what I did there is I stood in a gap, in a doorway, and I made a sound. And that sound was able to travel out, and then when I went around the corner and I made the same sound, that sound was able to bend around the corner and it was picked up by my microphone. So both light and sound are able to bend around corners. Well, we've learned that sound is a wave, and that must mean that light also acts as a wave. We also learned that sound is a longitudinal wave. And as it turns out, light is actually going to be a transverse wave. Transverse and electromagnetic. We'll learn about electromagnetism in a different unit. What we call light, electromagnetic radiation. It sounds scary, and it can be quite powerful, but really we get bombarded with electromagnetic radiation every single day. So if light is a wave, a transverse electromagnetic wave, that must mean that light has properties like sound did, like our amplitude, our wavelength, our frequency, and our period. We're going to save amplitude for later, but for now let's look at lambda and frequency here, wavelength and frequency. When we're looking at sound, the wavelength or the frequency, whichever one, the wavelength or the frequency determined the pitch of the sound, or how high or low it sounded. Remember that these two are related by the equation velocity is lambda times frequency. So as one of them goes up, the other one goes down. So if we talk about wavelength, we're simultaneously talking about frequency. If we're talking about frequency, we're also talking about the wavelength. And the frequency and the wavelength of sound determined the pitch. But what does frequency or the wavelength of light determine? Well, that actually is going to determine the color that we see. So if we look at the color red, red is going to have a longer wavelength. Remember, the wavelength is crest to crest. Than say the color blue. Blue will have a shorter wavelength. And green and all of the other colors in there lie somewhere in the middle. And we can even put a number on these wavelengths. The wavelength of red is equal to 700 nanometers. And the wavelength of blue is actually equal to 400, around 400 nanometers. And in between this range is the spectrum of visible light that we see, the rainbow colors that we see. Our eyeball is specifically adapted to see the colors in this spectrum here. And we'll learn about that a little bit later. But what happens about the wavelengths that we can't see? What if the wavelength becomes very, very, very large, something like 100 or 1000 meters, not nanometers anymore? Or what if the wavelength becomes very, very small, something like 1,000 times 10 to the negative 1,000 nanometers? What happens to the color that we observe then? Well, what we've done is we've put all of these wavelengths on something that's called the electromagnetic spectrum. There's a nice diagram in your book of the electromagnetic spectrum here. So let's start all the way down at gamma rays, where the wavelengths are the shortest, around the size of a proton or a nucleus. That's where it starts, at gamma rays. As we move up from gamma rays, about the size of an atom or a molecule, we have what are called X-rays. You've probably had X-rays before when you're at the doctor or the dentist, but a famous application of X-rays, they actually used X-rays to discover the double helix structure of DNA. Thank you, Rosalind Franklin, for that. After X-rays about the size of a virus, we have ultraviolet light. Ultraviolet light is something that's very important to our pollinator friends, like the bees and the butterflies. Their vision is actually shifted. They're not able to see the reds and the oranges and perhaps the yellows, but they are able to see into the deeper ultraviolet part of the spectrum. That helps them locate pollen. And then we can get into the visible light spectrum, the part of the spectrum that we as humans observe every day. And it turns out, if we think about our sun actually emits all of these types of radiation, all different wavelengths. But the wavelength that it emits the most of is in this visible light spectrum right here. So when we were evolving on this earth, our eyeballs, the light buckets on our faces, evolved to see this visible light, or the light that the sun gives off the most. We didn't have a need, we weren't pollinators, so we didn't have a need to see in the ultraviolet region. We just had a need to see in the red through blue region there. If we go above, up to the size of about a cell, we get into the infrared region. Here's a picture of a remote control, and then here's a picture of the remote control in the dark with me pressing a button. And it turns out your phone camera is sensitive to this infrared light that remote controls use. If we go up one more, about the size of a bee or a baseball, we're in the microwave region here. And a good visual representation of how big a microwave is just to go look at your microwave. That little protective screen that's on the front door of your microwave. Those holes are just a little bit smaller than microwaves are. And that's so the microwaves don't come out and start cooking you instead of your food. And then from about the size of humans to houses to planets to stars, we have our final biggest form of radiation, which are radio waves. Remember too that this is just a spectrum, and really these wavelengths can go on forever in both directions. And here we've only made these different distinctions of the wavelengths to help us organize different sections of the electromagnetic spectrum. But in reality, you have to remember that it's all the same type of wave. It's all electromagnetic radiation. It's all that transverse wave that we talked about before. But what is different is the wavelength, the size of the wave, that determines how it interacts with the physical world. And how it interacts with the physical world is different depending on the size of the wave. Also remember that light has a speed, and everything all the way down from gamma rays all the way up to radio waves will travel at the speed of light. The speed of light in a vacuum we call c, and c is equal to 3 times 10 to the 8 meters per second. We can use the wave velocity equation too to describe that.